Okay, so this week we are going to study the details on reverse bias current or PN junction diode, as well as the reverse bias breakdown event within PN junction diode. So the corresponding chapters for those contents can be found in chapter 6.2. So please take your own time to read all the sentences one by one in the chapter 6.2. Please do that. Then that would be very helpful for you to follow up, catch up my materials. All right. So before moving forward, let's take a look at before taking a look at this carrier concentration profiles given in this slide, please go back to the first page on this lecture note and think about how electrons and holes are distributed out under forward bias. So think about that, especially in the depletion region as well as near the depletion region, how electrons and holes are distributed out under forward bias. Well, if you have more time, please imagine how electrons and holes are distributed out under reverse bias as well. Think about that. While we are deriving the ideal diode equation in the last movie clip, we have learned the minority carriers are injected into the other side, right? The holes, which was a majority carriers in the P side, are injected into the N side, then the holes can be acted as a minority carriers in the N side. Then since there is not much voltage drop across the N side quasi-neutral region, so that the injected holes can be diffused out. That's the reason why we have used the minority carrier diffusion equation, which was mathematically described as a second order partial differential equation. So for given general solution, we tried to find out the coefficient to build up and complete the general solution form. For that purpose, we have derived the two boundary conditions at x of xn in the n-type quasi-neutral region, as well as at x of infinity. So from those processes, we can derive fully the ideal diode equation. But now is a good timing for you to imagine how electrons and holes are distributed out across the p-n junction diode, especially in the depletion layer, especially near the depletion layer edge. So think about that. Just if you have some time, please stop here and think about it. And if you have any blank A4 size page, then try to draw your own carrier concentration profile under forward bias as well as under reverse bias. Okay? Okay, now let's move on to the answer here. So carrier concentration profiles under forward bias. So here, y-axis, I have drawn two different y-axis to emphasize how the holes and electrons are distributed out at each quasi-neutral region. Here, p side, and this is n side. Okay, and y-axis indicates electron concentration or hole concentration. Well, definitely in low scale. So this one small line indicates, say that is 10 to the 18, then second one is 10 to the 17, and blah, 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 blah. Okay, so under forward bias, many holes in the P side can be injected into the N side. However, the total amount of hole, delta P, in the N side can never significantly affect the majority carrier concentration. In this N side, the electron concentration can never be significantly affected by the injected holes from the P side. Okay, so this was described as low level injection as well. Once electron has been arrived at x of xn or xn plus uh, maybe near the depletion layer, then they should begin to diffuse out. So the holes are now diffusing toward the other opposite side of a n-side quasi-neutral region. Well, in the end, because of too many electrons available in n-side, so all the holes injected should be recombined with electrons. But before all the holes are annihilated with electrons, there should be a certain, I mean, in this region, I would say from xn to xn plus alpha, in this region, some amount of holes would be accumulated uh, more than the equivalent hole concentration in the n side because a small amount of holes are injected near the depletion layer. So maybe near the depletion layer, suppose that from here to that, the injected holes would be accumulated in this region. So we may imagine the hole in n side at non-equilibrium. So that is a reason why I have denoted as a piece of n. So certain amount of hole would be injected. So this line indicates a piece of n, minority carrier concentration at non-thermal equilibrium. Okay, but this value should be asymptotically approaching to the piece of n naught value that is described as n sub I square over n sub d. In n side, the major suppose that the n sub d has been dumped into the n side so that the majority carrier concentration in n side at thermal equilibrium should be equal to the n sub d. And that value should be identical to the n sub n under forward bias because of the low level injection. So the majority carrier concentration can never be affected a lot too much. Okay, so this equation is still valid. What about the minority carriers? Yeah, the whole the whole concentration in n side at thermal equilibrium can be obtained from mass action law. So you can use n naught n sub I square. So instead of n naught, you can plug in the nd and I square. So Pn naught is identical to the ni square over n sub d. So that value you can find it out here. However, many holes under forward bias has been injected into the n side. A certain amount of holes should be accumulated, but those accumulated holes should be diffused into the n side, and in the end, they're gonna be recombined with majority carriers, which is electrons in n side. Okay. All right. So let me erase my note and take a look at how minority carriers are distributed out near the depletion layer. Okay, and this line should indicate the minority carrier concentration in n side, which is p sub n. And in the end, this value would be equal to the p sub n naught, that is identical to the ni square over nd. And this value should be identical to the n sub n naught, and that should be nd. If you would like to take into account the acceptor concentration in n side, you should do this. Instead of nd, you can use nd minus na, as well as here, nd minus na, if you know the acceptor concentration in the n side. Okay. All right, but usually n sub d is much higher than n sub a, so you can simply ignore n sub a term. All right, now similarly, you may imagine how electrons are distributed out in the p side quasi-neutral region. I mean the here. So under forward bias again, many electrons should be injected into the p side quasi-neutral region near the depletion layer. Then certain amount of electrons, which is minority carrier in p side, should be accumulated near the depletion layer. However, those injected electrons should diffuse out toward the left-hand side edge of the p side. And since there are humongous number of holes available in p side, which is my majority carrier, so those injected electrons should be annihilated. I mean, simply speaking, killed by many holes. So I mean, the electron hole pairs are recombined a lot, then in the end, the injected electrons would be gone away. So near the depletion region, those injected electrons would be alive and they move towards the left-hand side edge of the p side by diffusion mechanism. Again, there is a not very strong electric field available in p side quasi-neutral region because think about the series connection of three different registers across p-n diode, and since in the depletion region there is no electrons holes available at all, therefore in terms of resistivity, you know, the resistivity in depletion layer is much higher than the resistivity in the quasi-neutral region in both p side and n side. So we can, once you apply a certain amount of voltage across p-n diode on the p side, then all the voltage should be dropped across the depletion layer. So in that sense, the resistance value in the p side and n side is almost zero. In other words, there is not too much voltage drop, so that the electric field is almost zero. That's the reason why we can ignore the drift mechanism when we are explaining how the injected electrons can be moved in the p-side quasi-neutral region. So I hope all the students who are taking my lecture to fully understand what I have said. And if not, please review what I have told you in the last movie clips and try to do your best to read all the sentences in the chapter 6 and 5. Okay. Otherwise, it would be much tough for you to catch up all the materials that I'm going to teach in the near future. Okay, please do that. All right. Now it's time. Let's, now let's think about the carrier concentration profiles, not under forward bias, but under reverse bias. So here is the answer. So in the same x-axis and y-axis. Y-axis indicates electron concentration, hole concentration in the linear scale in this case. Previously, I have used the low scale, but herein I have used the linear scale. And x-axis indicates the displacement across the p-n junction diode. Okay, so under reverse bias, you know, all the electron holes can never be dived into the depletion layer because of what? Yes, because of the increased energy barrier. So all the holes can never get into the p-n side. Similarly, all the electrons available in conduction band can never overcome the energy barrier height formed between p side and n side, so that all the electrons can never be injected into the p side. So in terms of majority carriers action, there is no actions. However, as we have learned, the minority carriers in p side, which is electron, and the minority carriers in the n side, which is a hole, so they are freely without any energy barrier height, energy barrier, and without any energy barrier, minority carriers in p side, electron, and another minority carrier in n side, which is a hole. So those carriers would be freely moved into the other side. So that is the physical origin how current can be formed under reverse bias, but very small, negligibly small amount of current can be formed across PN diode under reverse bias. So most of the as described here, depletion of minority carriers at edges of depletion region. So I mean the here and there. So near the depletion region, from the edges, I mean the xn plus maybe one diffusion length here LP, and here minus xp minus L sub n. So this Ln indicates the diffusion length of electron, which is the minority carrier in p side, and this L sub p indicates the diffusion length of hole in the n side, which is another minority carrier. So in this reason, as we have learned, the thermally generated electrons and holes, in this electrons and holes would get into the depletion layers, so that in terms of the hole concentration near the depletion layer edge, the hole concentration P in the N side should be smaller than the P and naught, okay? Because thermally generated holes would be diffused toward the depletion layers, so part of the holes would be lost, right? So you may reasonably understand, figure out how the hole concentration in the N side under reverse bias, definitely, okay? Under reverse bias, and you may guess the electron concentration profile in the p side, okay, under reverse bias. Okay, so as we have learned, the saturation current in the diode under reverse bias can be obtained and explainable with the help of drift mechanism of minority carriers across the junction. And this drift current can be fed by diffusion mechanism only of the minority carriers toward the junction. Okay, so all the uh, minority carriers to be supplied toward the junction should be obtained from the thermal generation, where in this regime, here and there. Okay, all right. I guess it's a good time for you, for me, to hand out the homework problem set. So this is only for your homework. So I'm going to skip this slide, but please go back to the textbook and read out the corresponding sentences. Then I hope once you have well trained yourself with my last movie clips, and if you have any chance to fully derive all the detailed equation for ideal diode, then it it is not very tough for you to figure out the physics happened in p-n junction diode under forward and reverse bias. But you may have a chance to think this: how come very complicated for I have whenever I have to, I mean, the your question in your mind is this: how complicated to derive the ideal diode equation? Is there any easiest way to get to the final, equation form for ideal p-n junction diode? Yes, it would be possible. So one of the ways are explained and dealt in this lecture note. So the title is Alternative Derivation of Formula for Saturation Current I sub naught. So some key equations are brought and described in this lecture slide. However, I would like to ask you to take a look at the details in the textbook, introduced in textbook, and hand out your own explanation and your own derivation steps for saturation current I naught. Well, in the end, you're gonna get this equation, okay? But please write down your own words, how to get to the final form of the saturation current I naught, okay? So that would be the uh, homework for this week. Okay, let's keep going on. I guess that would be good timing to stop here. And in the next movie clip, I'm going to explain the junction breakdown. Okay, so some breakdown mechanisms such as avalanche breakdown and Zener breakdown, tunneling breakdown. So avalanche, let's take a look at avalanche breakdown mechanism to be explained, and tunneling or Zener breakdown mechanism are followed. So take your time and try to preview what would be introduced in the next movie clip. Then that would be very helpful for you to catch on my materials. So let me stop here and see you in the next movie clip. Thanks for your attention and don't forget to hand out your homework.